the department ID property. The inner loop traverses the item members within each of the groups that have been created in our query based on the department ID property. Great! We could also include the order by operator within our query like this. Let's run the code. Great! We can implement the same query using method syntax using the toLookup extension method like this. Great! We can also include sorting functionality through the order by operator through the implementation of method chaining like this. Great! Note that the toLookup method performs the same operation as the group by operator. The only difference is the execution of the group by operation is deferred, whereas the execution of the toLookup operation is executed immediately. We discussed deferred execution and immediate execution in the previous part of this video series. For more information on deferred execution and immediate execution, please view the second part of this video series. A link to this video has been included below in the description. Note that the results returned from a group by operation and a toLookup operation return a group contained in a special type of collection that implements an iGrouping generic interface . So let's look at the all, any, and contains quantifier operators. Let's first look at the all and any operators. Let's create a variable named annual salary compare and assign it with a value of 20,000. Let's implement a block of code related to the all operator. Let's implement a similar block of code related to the any operator. So, the all and any operators return a Boolean value. The return value will equal true if the elements in the relevant collection satisfy a condition passed to the relevant method. This condition can be passed in the form of a lambda expression. This query will return true if all employee records have annual salary property values that are greater than 20,000. This query will return true if one or more employee records have an annual salary property value that is greater than 20,000. Let's run the code. Great! This is an expected result. Let's change the annual salary compare variable to 100,000. Great! And let's change the annual salary compare variable to 40,000. So let's move on to the contains operator. So we want to be able to assess whether an employee record exists within our collection of employee records. The contains operator will return true if we pass in an object that is equal in value to an object within the relevant collection. To understand how the contains operator works, let's create an employee record that we know matches an employee record within the employee list collection. Let's copy this record for the employee named Douglas Roberts that is a member of the relevant employee collection. And paste it in our main method. Let's name the variable that stores a reference to the employee record we wish to find within the employee list collection, search employee. So how can we assess whether the employee record pertaining to Douglas Roberts exists within the employee list collection? We can use the contains extension method. We can simply pass the variable we named search employee to the contains extension method, which we have invoked on our employee list collection object. So the contains method returns true if the search employee object matches any of the objects within the employee list collection, and false if the search employee object does not match with any of the objects stored within the employee list collection. So let's write code to write an appropriate narrative to the screen based on the Boolean value returned by our query. Let's run the code. And this is not the result we expected because we literally copied and pasted the code representing one of the employee objects that has been added to the employee list collection from our data class to the main method as our search object. So Y is our output indicating that the search employee object does not match any of the objects stored within our employee list collection. This result is unexpected. The answer is that the compiler knows how to compare built-in C# types like, for example, integer or bool. The employee type is a user-defined type or custom type. We need to tell the compiler how we wish to compare two objects of type employee to establish whether two employee objects are equal. So we can do this by creating a class that implements the generic iEqualityComparer interface. The iEqualityComparer interface is a member of the system.collections.generic namespace. We have already included a using directive to this namespace within our code. So let's create a class named EmployeeComparer, and let's indicate that we want the EmployeeComparer class to implement the iEqualityComparer generic class that is strongly typed with the employee user-defined type. So let's hover our mouse pointers over the red squiggly line and create the stubs for the methods that we need to implement, like this. So two method stubs have been generated, one named equals and the other named getHashCode. So the getHashCode method is used for the purpose of uniquely identifying an object. We can implement the code for the getHashCode method by returning the hash code of the ID property of the relevant employee object, like this. The equals method must be implemented in a way that establishes how we wish employee objects to be compared when determining whether two employee objects are of equal value. So let's say that we are satisfied with comparing the relevant employee objects based on their ID, first name, and last name properties to establish equality between the relevant employee objects. So we can achieve this with the following code. If the relevant properties are equal, return true, else return false. So we are already passing in the search employee object to the contains method. Let's also pass a newly instantiated object of type EmployeeComparer to an overload version of the contains method, like this. And now we are telling the compiler how we want to compare our employee search object with the objects stored within the employee list collection. Let's run the code. And this is an expected result. The contains method now returns true as expected because our search record matches the employee record for Douglas Roberts within the collection on which we are performing our search. Great. So now let's look at the of-type filter operator. So before we use the of-type filter operator in our code examples, let's create a method named getHeterogeneousDataCollection. Heterogeneous in this context, of course, is referring to the storage of objects of multiple different data types within the same collection. So we can store objects of multiple different data types in an array list. Note that Microsoft does not recommend using array lists for new development. It is far better to use strongly typed lists to store collections of data. For more detail as to why strongly typed lists are recommended, please view a video on generics created by this channel. A link to this video has been included below in the description. So, a use case where we could apply a link query on an array list could be perhaps we have a legacy piece of code that includes an array list containing objects of multiple types, and we need to filter the relevant array list based on specific types. We can achieve this using the of-type link operator. We'll look at how we can do this in a bit. Let's first add some made-up data to an array list. So the array list stores integers, strings, objects of the employee user-defined type, and objects of the department user-defined type. Let's go to our main method and write code to use the of-type operator to query this array list based on specified data types. Let's query for all string values in our array list. Great. So let's query all integer values in our array list. Great. Let's query for all objects of the employee user-defined type. Great. Let's query for all objects of the department user-defined type. Excellent. So you can see how we can query an array list for objects of a specified type using generics and the of-type operator by passing in the relevant type between angle brackets like this. This will return those objects within the array list that are of the specified type. Let's move on to the element operators. Let's look at the element at or default, first or default, last or default, single, and single or default element operators. So let's first look at the element at operator. So the element at operator is used for querying for an item in a collection that resides at a specified ordinal location within the relevant collection. So we can pass an integer value representing the relevant element's location in the relevant collection into the element at method to return the desired item's value from the relevant collection, like this. Great, and our query has returned the value for the relevant element. But what happens if we pass in a value representing a position in the relevant collection where an element does not exist? So let's try this. Let's pass in a value of 8. Right, so it is important to note that no item exists within the relevant collection at ordinal position 8. So in this case, an argument out of range exception is thrown. This brings us to an important point about the difference between the element at and the element at or default method. If we replace the element at method with the element at or default method, and we query the relevant collection for an item at a position where the desired item does not exist within the relevant collection, the element at or default method does not throw an exception, but rather returns the default value for the desired item's relevant data type. Let's briefly discuss what we mean by a default value for a particular data type. The C# language associates default values for C# data types. So if, for example, we are querying a collection of integers using the element at or default method for a value that did not exist at the specified location in the relevant collection, the element at or default method would return the default value for the integer data type, which is a value of 0. The integer value of 0 is the default value for the integer data type in C#. If, however, we are querying a collection containing a reference type object like an object of our user-defined type employee, the default value returned by the element at or default method would be null. Null is the default value for reference type data types like user-defined types or the string data type. For more detail regarding default values in C#, please navigate to this URL. So let's use the element at or default method to query the relevant collection of employees for a value at position 8, i.e. where no employee object is present within the relevant collection. We can then write code to check if the returned value is null. And you can see that an exception is not thrown and no results are outputted to the screen, which is an expected result because the query returned a null value. Let's pass in a value of 2 and then 1, and in both cases the appropriate result is outputted to the screen. So let's write code to output an appropriate narrative to the user based on the value returned from the element at or default method. So let's pass in a value of 12. The output indicating that the return value is null, i.e., the employee object does not exist in the collection, is outputted to the screen. This is an expected result. Great. So the first operator returns the first element in a collection if no condition is specified. We have the option of passing a condition to the first method, or we can leave the brackets following the first method empty. If we do not specify a condition, the query will return the first element in the relevant collection. If a condition is specified, the first operator will return the first element in the collection that satisfies the specified condition. We can specify a condition in the form of a lambda expression. Right, to prove this, let's first create a strongly typed list of integer values. So if we query this collection using the first operator and don't provide a condition passed as an argument to the first method, the query returns the first item in the collection as expected. So let's pass a condition in the form of a lambda expression to the first extension method. So this condition is simply querying the collection for the first even number in the collection. Let's run the code. Great. But now what happens if we alter the collection of values so that no value satisfies the condition, i.e. no even numbers exist within the relevant collection? An invalid operation exception is thrown. So if we don't want an exception to be thrown, we can replace the first operator with the first or default operator. As you may have guessed, where no items in the relevant collection satisfy the relevant condition, this method will not throw an exception, but will rather return the default value of the relevant data type. We know that the default value for the integer data type is 0. Let's write code to output an appropriate narrative to the screen if the relevant condition is not satisfied. Let's run the code. And this is an expected result. So let's include an element in the relevant list that does satisfy the condition. Excellent. So the last and last or default operators work in much the same way as the first and the first or default operators. The only difference is that the last item in the collection is returned where no condition is specified. The last item that satisfies a specified condition in the collection is returned when a condition is specified. The last method will throw an exception if an appropriate element is not present within the relevant list. We can use the last or default method rather than the last method to return the default value for the relevant data type in the case where an appropriate element in the relevant collection is not present. Great! So let's move on to the single and single or default element operators. The single operator returns the only element in a collection or one element that satisfies a specified condition from a collection. We have the option of passing a condition into the single method through the use of a method overload, or we can leave the brackets following the single method empty, which means we have chosen not to pass in a condition into the single method. If we choose not to pass in a condition into the single method, and there's more than one element or 0 elements in the collection, an invalid operation exception will be thrown. If, however, there's only a single element in the collection, the value for this element will be returned by the query. If we do choose to pass in a condition and 0 or more than one element satisfies the condition, an invalid operation exception will be thrown. If we pass in a condition to the single method and only a single element satisfies the condition, the value for this single element will be returned from the relevant single operation. Let's apply the single operator to a collection of employees. Let's first modify the data for our list of employees so that only one employee element exists within the relevant employee collection. Let's write code using the single operator to query the relevant employee list. Great, this is an expected result. Let's now include the employees that we just commented out back within the relevant employee list. Let's run the code. And an invalid operation exception is thrown as expected. This is because more than one employee resides in the list. If there is only one item in the relevant collection, the value for this item is returned. If there are 0 items or more than one item in the collection, and a condition is not specified for the single operator, an invalid operation exception is thrown. So let's test the single method, and this time specify a condition where one item within the relevant collection satisfies the specified condition. Great! Let's specify a condition where more than one item in the relevant collection satisfies the specified condition. As you can see, an invalid operation exception is thrown. So let's test the same scenario, i.e., more than one element in the relevant collection satisfies the specified condition, but this time let's use the single or default method. That's interesting. So note, where more than one element satisfies the specified condition when the single or default method is applied in the relevant query, an invalid operation exception is thrown, just like when the single method is applied to perform the same operation. So we can use the single or default method instead of the single method if we don't want an exception to be thrown under the scenario where no elements exist within the collection. The default value for the data type will instead be returned by the query. If a condition is specified for the single or default method, and no elements satisfy the condition, the same result will be produced, i.e., the default value for the data type of the element stored in the collection will be returned by the query. If a single item is present within the relevant collection, and the single or default method is applied to perform a query against the relevant collection, the single element's value that exists within the relevant collection will be returned by the query. Hi, and welcome to the fourth and final part in this video series on the LINQ technology using C#. This video is also part of the 7th tutorial in an advanced C# course. This video is a continuation of the previous 3 videos in this video series on LINQ, so I recommend viewing the previous 3 videos in this video series before viewing this video. In the previous video in this series, we looked at code examples where certain LINQ operators were implemented to query and transform data. This video is a continuation of the previous video in this series, where we'll create code examples using some of the other LINQ operators to gain a broader understanding of what can be accomplished using the LINQ technology in C#. So in the previous videos in this series, we have created code examples using the following LINQ operators. The sorting operators, order by descending, and then by descending. The grouping operators, group by and toLOOKUP. The quantifier operators, all, any, and contains. The filter operators, of type and where. The element operators, element at or default, first, first or default, last, last or default, single, and single or default. The join operators, join and group join. We have already looked at the select projection operator, and we'll also look at the select operator in this video, and in addition to this, we'll also look at the select many projection operator. So in this video, we'll look at the following link operators. The equality operator, sequence equal. The concatenation operator, concat. The set operators, distinct, except, intersect, and union. The generation operators, default if empty, empty, range, and repeat operators. The aggregate operators, aggregate, average, count, sum, and max. The partitioning operators, skip, skip while, take, and take while. The conversion operators, toList, toDictionary, and toArray. And lastly, the projection operators, select and select many. We'll also look at the following keywords that are useful when used in queries implemented in query syntax, namely the let and into keywords. We have looked at the select projection operator already in previous videos, but we'll look at this operator again in this video, as well as look at the select many projection operator. We'll then be able to gain an understanding of the difference between the select and the select many projection operators. As in the previous videos, I'll be demonstrating the code examples on my Mac platform. If you are using a Windows platform to follow along, the experience of creating these code examples will be almost exactly the same. So the fact that I'm using Visual Studio for Mac should not be a barrier for a learner using Visual Studio for Windows to follow along with the creation of these code examples. Okay, so let's create a .NET Core console project. So the official release of .NET 5 has now been released. So I'll be running this project using the new .NET 5 .NET Runtime. For more information on the significance of the .NET 5 runtime, please view the second part of this advanced C# course. I've included a link to this video below in the description. The project we created in the last video was named linkexamples_2. Let's name this project linkexamples_3. So as we did in the previous video, let's navigate to this URL where we can access code on GitHub for the project that was created in the previous video of this series. Here we can copy the data-related code that we created in our previous project so that we can reuse these data-related classes in this project. Let's click the directory icon labeled linkexamples_2. Let's then click the file icon labeled program.cs. Let's copy the class named employee and paste the contents of our clipboards to our new project. Let's do the same for the department class. And the data class. Okay, so we won't be using the getHeterogeneousDataCollection method that resides in the data class in this video, so let's delete this method. Let's refresh our memories about the classes we have just copied and pasted from GitHub. The employee class contains a definition for an employee record. The department class contains a definition for a department record. The data class contains hard-coded, made-up data for employee records and department records. The employee records are stored in a generic list strongly typed as employee. The department records are stored in a generic list that is strongly typed as department. We can access the data stored in the employee list collection from calling client code, in this case, this will be the main method, by calling the static method named getEmployees. We can access the data stored in the department list collection by calling the static method named getDepartments. Note that the data class in which these methods reside is a static class. Let's navigate to the main method, and before we create our example code, let's add the appropriate using directives. First, let's add a using directive to the system.collections.generic namespace. The generic list type is a member of this namespace. Let's also add a using directive to the system.link namespace. Once we have added our system.link using directive, we can access our link operators on collection types that implement the IEnumerable interface. So, for example, list types implement the IEnumerable generic interface. So we are able to access extension methods stored within the enumerable static class, which is a member of the system.link namespace, by including a using directive to the system.link namespace. The queryable static class also includes link extension methods and is a member of the system.link namespace. For more information on how extension methods work in C#, please view the first video in this video series. A link to this video has been included below in the description. Before we get started creating our code examples, I want to draw your attention to what might be an issue for Visual Studio for Mac users. When we run our code interactively through Visual Studio for Mac, by default, the output may appear in the terminal console window within Visual Studio for Mac, like this. This is absolutely fine for testing code, but you may prefer to present the output externally, i.e. in a terminal console window outside of Visual Studio for Mac. If you would prefer to present your output externally, i.e. outside of Visual Studio for Mac, please navigate to Visual Studio for Mac Preferences, then under the heading marked Other, select the item labeled Terminal. In the right pane of the relevant dialog box, ensure that the Enable Integrated Terminal checkbox is unchecked. This is obviously not a functional issue, it really comes down to personal preference. Let's define a generic list variable named employee list that is strongly typed as employee, and let's assign the collection of employee records returned by the data.getEmployees static method to the employee list variable. Let's define a generic list variable named department list that is strongly typed as department, and let's assign the collection of department records returned by the data.getDepartment static method to the department list variable. Okay, so we are now ready to query and transform data using LINQ. So let's start with the equality operator, sequence equal. So the use case here is we want to compare two lists of data, and we want to know if these two lists contain elements of equal value and each element in each of the relevant lists are stored in the same order. If each item in each list matches in terms of value and order, the sequence equal method will return true. If any of the items in each of the relevant lists does not match in terms of value and order, the sequence equal method returns false. Let's create a generic list named integer list1 that is strongly typed as integer. Let's copy and paste this line of code to the next line. Let's change the name of the second list to integer list2. Let's run the code. And the sequence equal method returns true, because the values and sequence of elements in integer list1 is identical to the values and sequence of elements in integer list2. Let's change the order of the items in integer list2 so this sequence of values is not equal to the sequence of values stored in the list named integer list1. Let's run the code, and this is an expected result. Let's change integer list2 once again for good measure. And this is an expected result. Great. So let's change the data in integer list2 so that the order and values in the lists are equal. And now the result is true, which is an expected result. That was pretty straightforward, i.e., comparing two sequences of values of a primitive data type, i.e. the integer data type. But what if we want to test this type of equality between two lists that are strongly typed with a complex type, like for example our employee user defined type? So let's define a variable named employee list compare as a generic list type that is strongly typed as employee, and let's assign the collection returned from the data.getEmployees static method to our employee list compare variable. Let's run a sequence equal operation and compare the values stored within our employee list compare collection with the values stored within the employee list collection. So one would expect the result of this sequence equal operation to return true because both collections contain exactly the same data. Let's see what happens. Oh, and false is returned. The reason why false is returned is because we need to tell the compiler how to establish equality between objects of the relevant complex type, i.e. in this case, the employee type. So we achieved this in the previous video in this series by implementing the built-in iEquality comparer generic interface. So let's copy the relevant code for this that we implemented in the previous video in this series. Let's navigate to the GitHub repository at this URL that contains the code we created in the previous video in this series. Let's copy the class named employee comparer to our clipboards and paste the contents of our clipboards to our projects like this. We have red squiggly lines, so let's fix this by bringing in the appropriate using directive. So here we have implemented a class named employee comparer that implements the generic iEquality comparer interface that is strongly typed as employee. This gives us a way of telling the compiler how we want objects in our lists of type employee to be compared when determining equality between the relevant objects. So we are explicitly doing this here in the equals method, where we are comparing the ID, first name, and last name properties between two employee objects. We are returning true if the relevant properties of the relevant two objects are equal, and false is returned if any of the relevant properties of our two objects are not equal. Within the getHashCode method, we are returning the hash code of the ID property of the relevant employee objects. For more information on hash codes, please navigate to this URL. So now let's go to our main method, and we can pass in a new instance of the employee comparer class to an overloaded version of the sequence equal method. This object will tell the compiler explicitly how we want our employee objects to be compared. Let's run the code. And now the sequence equal operator works as expected. So note that we need to tell the compiler how we want objects that are defined as complex types to be compared when determining equality between the relevant objects. We can do this by creating a class that appropriately implements the iEquality comparer generic interface. Great! Let's move on to the concatenation operator named concat. We can use the concat operator to append one collection of data to another collection of data. So let's see the concat operator in action. Let's create a collection of integer values. Let's then create another collection of integer values. Let's append the second collection of integer values with the first collection of integer values using the concat operator. Let's write code to output the results of this concatenation operation to the screen. Let's run the code. Great! Let's do another example, but this time let's append a collection that contains a collection of objects of a complex type to another collection of objects of the same complex type. The complex type we'll use in this example will be our employee user-defined type. Once again, we can use the concat operator to achieve what we want here. Let's run the code. Great! Let's move on to the aggregate operators. Let's first look at the aggregate operator. Using the aggregate operator, we can perform a custom operation on values within a collection. Let's say we have a requirement where we need to provide a total for the annual salaries of our employee records. We also need to include the addition of an appropriate annual salary bonus in the final result. Let's say a manager gets a bonus of 4% and employees that aren't managers get a bonus of 2%. So let's say we have a use case where we need a result that is a total of all employee annual salaries, which must include each employee's bonus. We can take this added complexity into account when totaling up our employee annual salaries through the use of the aggregate operator. So the first argument is the seed value. So let's provide 0 for this argument. Using this argument, we are initializing the value that will be returned by our aggregate operator. The next argument is of a delegate type, where we can include the logic for our aggregation functionality in the form of a lambda expression. So as you can see in our logic for the relevant lambda expression argument, we are checking to see if the relevant employee is a manager, whereby we need to add a bonus of 4% to the relevant employee's annual salary. If the employee is not a manager, we need to add a bonus of 2% to the relevant employee's annual salary. We can then include the appropriate bonus amount in our calculation. So we are adding up all employee annual salaries, which includes each employee's appropriate bonus. Let's run the code. Great! Say we want to output a comma-delimited string from our employee list collection. Each delimited item containing the employee full name, a dash, then the employee annual salary. Each annual salary must include the appropriate bonus. We also want to include a label preceding the comma-delimited string. We can achieve this using the aggregate operator like this. The first argument is the label, where an appropriate value could be something like employee annual salaries including bonus. Then the logic of our aggregation functionality can be expressed in a lambda expression for the second argument, like this. We can apply the same logic to include appropriate bonuses from our previous example. Let's run the code. Great, but we have a slight issue where a comma is presented at the end of our string. We don't want this comma in our final result. We can express this by passing a lambda expression as our third argument to an overloaded version of the aggregate operator. This argument allows us to perform a final operation on the results produced by the lambda expression passed in as the second argument. We first need to include another data-type argument with an angle brackets following the aggregate method to declare the data type of the final output, i.e. provided by the lambda expression we are passing in to the last parameter of this overloaded version of the aggregate method. In the lambda expression passed in as our final argument, we are using the substring method to remove 2 characters from the end of the result, which means a comma and a space will be removed. This result is what we want. Excellent. So let's move on to the average aggregate operator. So to find the average annual salary for a list of employees, we can apply this code. Great. If we want to find the average salary for all employees in the technology department, we can use method chaining and the where operator to achieve this, like this. Great. For more information on method chaining, please view the second part of this video series. Let's move on to the count aggregate operator. So if we want to know how many employee records we have in our collection of employee records, we can apply the count operator like this. Great. If we want to know how many employees are members of the technology department, we can pass in a condition as an argument to the count operator. The condition that is passed in as an argument to the count method can be expressed in the form of a lambda expression. Great. Let's move on to the sum aggregate operator. So let's keep this simple. We just want the sum total of all annual salaries of all employee records stored in our employee list collection. We can apply the sum operator to achieve this. Great. Let's move on to the max aggregate operator. So if we want to return the highest annual salary property of all employee records stored in our employee list collection, we can apply the max aggregate operator in a LINQ query like this. Great! Let's move on to the generation operators, namely default if empty, empty, range, and repeat. Let's first look at the default if empty operator. So we can use the default if empty operator to return a new IEnumerable collection that when, for example, we apply the element at method on the new collection to check if the new collection is empty, the operation will return the default value for the relevant type used to strongly type the relevant collection. A query using, for example, the element at method against a collection returned from a default if empty operation will not throw an exception if the collection is empty. The default value of the type with which the relevant collection is strongly typed will instead be returned. For more information on default values for C# data types, please navigate to this URL. We'll see later how we can pass in a value to the default if empty method to specify our own default value that we'd prefer to be returned when, for example, the element at method is used to check if the relevant collection is empty, rather than the default C# value for the relevant data type. Let's look at an example using the default if empty method. So let's create an empty list of integer values. Let's perform a default if empty operation on this collection of integer values and assign the returned collection to a new collection of integer values. Let's use the element at operator and pass in 0 to the element at method to check if the collection is empty. You can see that the element at operator returns the default value for the integer data type, which is 0. This is an expected result. Let's create another example, but this time let's use the employee data type to strongly type our collections. As discussed, the default value for a reference type in C# is null. But as discussed, we can pass in a default value that we would prefer to be returned by, for example, the element at operator when the relevant collection is empty. So let's pass in an employee object where the ID property of the relevant employee object is set to 0. Null is not returned, as would be the case if we hadn't passed in a value to the default if empty method, because we have specified our own default value where the ID property of the default employee object is 0. Great. Similarly, we could have set the default value for our integer collection example by, for example, passing in 999999 to the default if empty method. Instead of returning the default C# value for an integer, which is 0, 999999 is returned. This is an expected result. Excellent. Right, let's look at the empty method. So we can use the empty method to generate a new empty collection. So for example, we want to create a new IEnumerable generic collection of employee records. We can do this by using the empty operator like this. Note, the empty method is not an extension method of IEnumerable or IQueryable like other LINQ methods. It is a static method included in the enumerable static class. So for example, we could instantiate a new empty generic list strongly typed with the employee user-defined type through the use of the empty method. We can then chain the toList conversion operator to this operation and return an empty generic list. We are using the toList operator to convert an IEnumerable generic collection that is strongly typed with the employee data type to a generic list that is strongly typed as employee. So for good measure, let's add a new employee item to our new list that we have generated through the use of the empty method and the use of the toList conversion operator. Let's write code to write the items, or in this case one item, stored in our new list to the screen. Great. Right, let's move on to the range generation operator. We can use the range operator to return a collection of values that are within a specified range. So let's clarify this with an example. We want to return a range of integer values in a collection where the first item in the range has a value of 25 and each subsequent item is incremented by a value of 1 until there are a total of 20 values in the relevant collection. We can achieve this by using the range method like this. In this example, the first argument specified is 25. This is the value of the first element, and the second argument specifies the number of elements to include in the relevant generated collection. When each item is added to the collection, it is incremented by a value of 1. So the second item will be 26, the third item will be 27, the fourth item will be 28, and so on. Let's run the code. Great. So using the range operator, we have generated a collection of integer values that fall within a specified range. Excellent. Let's say we want to generate a collection of a specified amount of elements where a value for each element in the collection is repeated. We can use the repeat operator for this purpose, like this. Great. Let's move on to the set operators, namely distinct, except, intersect, and union. Let's start with distinct. So let's say we have a strongly typed generic list that contains a list of integer values, some of which are repeating values. We want to perform a query against this list of integer values where we only want distinct values returned. We can achieve this by applying the distinct operator to our query like this. Great. Let's say that we have two collections of a specific type and we want to return elements with values in our first collection that are not equal to any of the values of the elements in our second collection. We can achieve this by using the except operator. Let's look at an example of using the except operator applied to two collections of integer values. So 1 and 2 are returned in our results collection because these values exist in our first collection and don't exist in the second collection. The values 3 and 4 exist in our first collection and also exist in our second collection. The values 5 and 6 exist in our second collection, and even though these items don't exist in our first collection, the except operator does not return these items as part of the results collection, because in this example, the except operator returns values that exist in the first collection and don't exist in the second collection. Let's try an example using complex types. Let's use our employee type. Let's create a generic list strongly typed as employee. Let's copy data that we know will exist within our employee list collection and add these items to the list we have named employee list 2. Let's add some additional items to the employee list 2 collection. Let's then call the except method on the employee list collection and pass in the employee list 2 collection as an argument to the except method. Then let's assign the results of this operation to an implicitly typed variable named results. We have of course used the var keyword to implicitly type our results variable. Let's write code to traverse the results and output the results to the screen. Let's run the code and see what happens. And this result is not expected. The output contains all items within the employee list collection. I would have expected that the items that were copied from the data class and added to the employee list 2 collection, as well as the other items that we added to the employee list collection, would be excluded from the results. The reason for the unexpected results is because we have not told the compiler how to compare employee objects when determining if one employee object is equal to another employee object. So how can we let the compiler know how we want one employee to be compared to another employee within our collections when determining equality between the two relevant objects? You may have guessed already how we can achieve this. We first need to create a class that implements the iEqualityComparer generic interface. We can then write code to establish how one employee object should be compared to another employee object when determining equality between the relevant objects. We have already included the code for this, which we applied when we created code to perform a sequence equal operation on 2 lists that were strongly typed as employee. So we have our class named EmployeeComparer that implements the iEqualityComparer generic interface. So we can reuse this class for our example that performs an except operation on 2 generic lists that are strongly typed as employee. So all we need to do is create a new object of type EmployeeComparer and pass this object into an overloaded version of the except method like this. Let's run the code. Great! This is now an expected result. Let's move on to the intersect operator. So we can use the intersect set operator to return a collection containing only those items that exist in the employee list collection that are equal to the items that exist within the employee list 2 collection. And now that we know we are comparing elements in 2 collections that are strongly typed with the employee complex type, we need to pass in a new object of the EmployeeComparer type, i.e. a type that appropriately implements the generic iEqualityComparer interface. This tells the compiler how to compare 2 objects of type employee when determining if the relevant employee objects are equal. Let's run the code. And this is an expected result. Great. Let's move on to the union operator. The union extension method requires 2 collections and returns a new collection that includes distinct elements from both the collections. We can again use the same data we have used in the previous two examples to test the union operator. Right, let's write the code for this. You will notice we are also passing in an object of type employee comparer to the union method. Let's test the code. Great! So let's see what happens in this example when we don't pass in an object of type employee comparer to the union method. You can see that duplicate records are included in the results as a consequence of not passing in an object derived from a class that appropriately implements the generic iEquality comparer interface. And of course, we know we have already created such a class. So let's ensure that we pass in our object of type employee comparer to the union method so that only distinct employee objects are included within our results. Excellent. So let's move on to the partitioning operators. These partitioning operators include the skip, skip while, take, and take while operators. Let's first look at the skip operator. Use the skip operator to skip over a given number of elements in a sequence and then return the remainder. So let's query our employee list collection using the skip operator. Let's skip over 2 of the elements stored in our employee list collection and return the remainder of the elements using the skip operator. Great, this is an expected result. Let's look at the skip while operator. Using the skip while operator bypasses elements in a sequence as long as a specified condition is true, and then returns the remaining elements. Let's see this operator in action. So the condition here is skip elements in our sequence of employee objects in the employee list collection while the relevant employee object's annual salaries are above 50,000. Great, this is an expected result. Just to make things a little bit more clear on how this operator works, let's add a new employee record to the employee list collection. This employee record has an annual salary of 100,000, which of course is above 50,000. Let's run the code. And you can see that while the condition is true, the items in the relevant collection are skipped, i.e., will not be returned from the query. However, all subsequent elements in the sequence will be returned once the condition returns false. Even though the last element in the relevant sequence has an annual salary property greater than 50,000, it is still returned, because the third element in the sequence caused the condition to return false. The fact that the last element has an annual salary above 50,000 and therefore causes the condition to be true doesn't mean that the last item will be returned by our query. Note that once the condition returns false, all items from that point will be returned from our query. Right, let's move on to the take partition operator. The take operator is used to return a specified number of contiguous elements from the start of a sequence. Let's see this operator in action. This is an expected result. Great. The first 2 elements in the relevant sequence of elements in our employee list collection are returned by our query. So let's move on to the take while partitioning operator. The take while operator returns elements from a sequence as long as a specified condition is true, and then skips the remaining elements. So let's use the same condition that we used in the skip while operator example. So here we are using the take while operator to return elements from the relevant sequence that have an annual salary above 50,000. So the first 2 elements in the sequence are returned by our query. As soon as the third element is evaluated and the condition returns false, the elements from that point onwards in the relevant sequence will not be returned by our query. So for example, the fact that the 5th element in the employee list collection has an annual salary property that is greater than 50,000 is irrelevant because when the third element causes the condition to return false, and in terms of the take-while operator this means that from that point onwards, the rest of the elements in the relevant sequence will not be returned by our query. Great! Let's look at the conversion operators toList, toDictionary, and toArray. So let's look at the toList conversion operator. A query written in query syntax will return an IEnumerable collection containing the results of the query. What if we need our results to be returned as a generic list? We can achieve this using the toList conversion operator. Let's create an example to clarify this point. So for this example, let's query our employee list collection for employee records that have an annual salary property greater than 50,000 using query syntax. Note the red squiggly lines here. This is because we are attempting to assign an IEnumerable collection to a variable of type generic list. The compiler is telling us that we have created a type mismatch. So we can use the toList operator to convert the IEnumerable collection returned by our query to a generic list by wrapping the relevant query in brackets, adding a dot after the last bracket, and applying the toList operator like this. So now you can see the red squiggly lines disappear because we have removed the type mismatch. Let's run the code. Excellent. As discussed earlier in this video series, wherever a toConversion operator is applied to a query, as we have done here, this causes the query to execute immediately, i.e., query execution is not deferred, it is executed immediately. So if we want to convert an IEnumerable collection returned from a query to a dictionary object, we can apply the toDictionary operator to the query. Let's create an example to clarify what is meant by this. So, as in the previous example, here we have a standard query written in query syntax to query our employee list collection for all elements where the relevant elements have annual salary properties that have values greater than 50,000. So this is a basic query that will return an IEnumerable collection. But what if we want to return a collection where each element has a unique key associated with the relevant element? We can do this by converting the query result to a dictionary generic collection type. So let's alter our code so that the IEnumerable collection returned by our query is converted into a generic dictionary collection. So within angle brackets after toDictionary, we need to pass in two data types. The first data type declares the data type of the value stored in the dictionary. The second data type declares the data type of the key that will be used to uniquely identify each element in the collection. So the first data type is of type employee, and the second data type is of type int. Note that we want each element to be keyed on the employee ID property. We can express this by passing in an appropriate lambda expression to the toDictionary method like this. So let's traverse the key values stored in our dictionary object using a for each loop. Note how we are able to use the key values to retrieve the values of each element stored in the dictionary. We are doing this by passing in the relevant key within square brackets to the dictionary object. Here we are outputting the key as well as each employee's first name and last name to the screen. And as you can see, we have each employee's ID, which we have designated as our key value, followed by the corresponding employee's first name and last name properties. Excellent. We have successfully converted a query result from an IEnumerable collection to a dictionary object. As discussed, when we call any of the toConversion operators on a query result, this causes our query to execute immediately. For more information on deferred execution versus immediate execution, please view the second part of this video series. For good measure, let's also create a result using the to-array conversion method. So if we try to assign the results of this query to a variable defined as an array of employees, the compiler complains of a type mismatch. The query result is returned as an IEnumerable collection and not an array of employee objects. To remove the type mismatch, we can apply the to-array method like this. Great. So let's discuss the let and the into clauses that can be applied when using query syntax to represent a LINQ query. Let's look at the Microsoft Docs for an overview of the let clause. This overview of the let clause can be found at this URL. In a query expression, it is sometimes useful to store the result of a sub-expression in order to use it in subsequent clauses. You can do this with the let keyword, which creates a new range variable and initializes it with the result of the expression you supply. Once initialized with a value, the range variable cannot be used to store another value. However, if the range variable holds a queryable type, it can be queried. So let's look at a basic example using the let keyword in a LINQ query. Let's say we wish to query our employees based on employee initials. Now we don't have an initials property for an employee record, but within our query, using the let keyword, we can extract the initials from each employee record's first name and last name properties and assign the result of this extraction process to a variable named initials, directly within our query using the let keyword. This allows us to use the initials variable in our where clause as well as reuse the initials variable within our select clause. Through the use of the let clause, we can also apply a condition, and based on the evaluation of that condition, store a value in a variable that can be used later in the query, like for example within a where clause. Here we have a condition where we need to add an appropriate bonus to the annual salary property, based on whether the employee is a manager or not a manager. If the employee is a manager, we need to add a bonus of 4% to the relevant employee record's annual salary property. If the employee is not a manager, we need to add a bonus of 2% to the relevant employee record's annual salary property. We can store the relevant annual salary plus bonus value for each employee record by assigning the value returned by a ternary operator to a variable. We have named this variable annual salary plus bonus. The let clause in this example enables us to reuse the annual salary plus bonus variable, both within the where clause and the select clause later in the query. Let's run the code. Excellent. Let's look at the into keyword. We can use the into keyword in a LINQ query to collate data within a group, and then after this operation, we are able to perform a filter operation within the same query, if required, on the grouped data through the use of a where clause. So for example, let's use a LINQ query to first create a group of high-earning employees based on a condition. Let's say that the employee must earn above $50,000 to fit into the relevant group. We can use the where clause at this point in the query to appropriately filter the relevant employee records and the into keyword to put the filtered data into the relevant group of high-earning employees. So we can use the into keyword to group the high-earning employees into a group named high earners. Let's say we then want to further filter this group of high-earning employees by management status. So we only want these employee records where the isManager property is set to true returned from our query. We want to know which of those high-earning employees are managers. So we can use another where clause within our query to filter the high earner group based on the relevant condition. We have used a where clause earlier in our query to create the group of high earning employees. Then once the group is created through the use of the into keyword, we can further filter the group of high earning employees based on each employee record's isManager property. So we are able to include another where clause in our query to filter the grouped data. Let's run the code. Great. So lastly, let's look at the select and the select many projection operators. In this video series, we have already looked at the select projection operator. So the focus in this example is on the select many operator. We want to know how it differs from the select operator and in what circumstances we may wish to apply the select many operator in a LINQ query. Let's navigate to a Microsoft Docs webpage to see what the Microsoft Docs say about these two projection operators. Projection refers to the operation of transforming an object into a new form that often consists only of those properties that will be subsequently used. By using projection, we can construct a new type that is built from each object. You can project a property and perform a mathematical function on it. You can also project the original object without changing it. Select projects values that are based on a transform function. Select many projects sequences of values that are based on a transform function and then flattens them into one sequence. To understand the difference between the select many operator and the select operator, let's modify our department class so that it includes a property that stores a collection of employees. We have already discussed that department records have a one-to-many relationship with employee records. So each department object will now store a collection of related employee records. Let's also alter the getDepartments static method that resides in the data static class so that the getDepartments static method accepts an argument containing a collection of employee objects. Then for each department object added to the department list collection within the getDepartments static method, let's include a query to return an appropriate collection of employees, i.e. those employee records that have a department ID property matching the ID property of the relevant department object. So let's go to the main method and pass in the collection of employees to the getDepartment method. So now the getDepartments method will return a collection where each department contains a related collection of employee records. So now, what if we want to query the department list collection for all employees? We can achieve this using the select operator, but when traversing the results of the select operation, we will need to use an outer and an inner for each loop, like this. In this scenario, the select many operator is better to use for this purpose. The select many operator is better in this case because we can use one for each loop to traverse the results of our query, unlike where we needed to use an additional nested for each loop to traverse the results of our query, where we used the select operator. Behind the scenes, as it were, the select many operator appropriately flattens the results. And this means we don't need to use a nested for each loop to traverse the results of our query. We are able to use one for each loop for this purpose. Excellent. So we have covered a lot of ground in this video series on link operators. I would encourage you to practice using these operators to become proficient in writing link queries. This is a very powerful technology and is used with Entity Framework to perform database queries in modern .NET applications. Entity Framework is now the recommended technology to use in .NET for implementing database-related functionality in .NET applications. If we navigate to this Microsoft Docs webpage, we can see this paragraph that states, Entity Framework Core is a modern, object-based mapper for .NET. It supports link queries, change tracking, updates, and schema migrations. EF Core works with many databases, including SQL Database, on-premises and Azure, SQLite, MySQL, Postgres, and Azure Cosmos DB. This makes Link a very important technology to learn for .NET developers. Link enables developers to write one set of code that can be applied to handle data-related functionality for multiple different data sources. In Link, expression trees are used to represent structured queries that target sources of data that implement the generic iQueryable interface. If you would like to delve deeper into expression trees, please navigate to this URL. So let's summarize what we have learned in our 4-part series on using the link technology in C#. In the first part of this video series, we created our own extension method to filter data. We also demonstrated how a lambda expression can be used to express a condition that can be passed into our extension method to filter the data and return the filtered results from a query. The reason we created the filter extension method is because Link is mostly made up of extension methods stored in 2 static classes, namely a static class named enumerable and a static class named queryable. We are able to access the extension methods within these static classes by including a using directive to the system.link namespace. The enumerable and queryable classes are both members of the system.link namespace. In the second part of this series, we demonstrated examples using the select, where, join, and group join operators. We also discussed the difference between when a query is executed with deferred execution or immediate execution. We discussed how a link query is executed with deferred execution, but we can make the link query execute immediately by applying a to-conversion operator to the query. For example, toList, toDictionary, or toArray. In the third video in this series, we demonstrated code examples using the following link operators. Sorting operators: order by descending, and then by descending. Grouping operators: group by and toLookup. Quantifier operators: all, any, and contains. Filter operators: of type and where. Element operators: element at or default, first or default, last or default, single, and single or default. In the fourth and final video in this series, we demonstrated code examples using the following link operators: the equality operator, sequence equal; the concatenation operator, concat; the set operators, distinct, except, intersect, and union; the generation operators, default if empty, empty, range, and repeat operators; the aggregate operators, aggregate, average, count, sum, and max; the partitioning operators, skip, skip while, take, and take while; the conversion operators, toList, toDictionary, and toArray. Projection operators: select and select many. In this video, we also looked at code examples using the let and the into keywords. I hope you have enjoyed this video series on using the LINQ technology in C#. Hi and welcome to the 8th part of this advanced C# course. In this video, we'll focus on the use of attributes in C#. For more content on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you'll be notified of future content. If you like this video at any point, please consider giving it a thumbs up. It will be greatly appreciated. So, let's discuss attributes. Attributes allow the developer to add metadata in a declarative way to program elements in code, for example, classes, methods, properties, parameters, etc. A declared attribute is instantiated into an object at runtime, and at compile time, we can declare attributes against program elements to provide additional metadata to relevant program elements. The developer is also able to declare global attributes against assemblies, and in doing so add or modify metadata about the relevant assembly. So, the developer can use attributes to add or modify metadata about a particular program element or the assembly itself. In this video, we'll also briefly look at reflection. Reflection is a technology that we can use to read the metadata provided through the use of attributes at runtime. We are then able to, for example, implement code logic based on the metadata provided through the use of attributes. We'll look at how we can do this later in this video. There are two broad categories for attributes: predefined attributes and custom attributes. Predefined attributes are built into the base class libraries in .NET. In this video, we'll look at two main types of predefined attributes: global predefined attributes and general predefined attributes. Global attributes, like for example assembly version attribute and assembly description attribute, facilitate adding and modifying metadata for an assembly. General attributes, like for example conditional attribute, obsolete attribute, and attribute usage, can be applied to appropriate program elements. We'll start by implementing a code example using the assembly version attribute and assembly description attribute, which are global attributes. We'll use reflection to read the relevant assembly metadata and output the assembly metadata to the console screen. We'll then implement a code example using the following general attributes: conditional attribute, obsolete attribute, and attribute usage. The attribute usage attribute will be declared on our own custom attributes that we'll create a bit later in this video. We'll use custom attributes and reflection to implement field validation functionality. We'll demonstrate how custom attributes can be created by creating classes that inherit from the built-in system.attribute class. Later in this video, we are going to create custom attributes as part of validation logic that imitates how the ASP.NET MVC framework provides flexibility to developers through the use of reusable validation-related attributes. This video sets us up well for the next video provided by this channel, which will be a demonstration of creating a basic ASP.NET MVC application on .NET 5. Right, let's create our code examples so that we can gain an understanding of attributes in C#. Let's create a .NET Core console application project. Let's name this project Attributes Examples. Let's ensure that we are using .NET 5 for this project. If you haven't yet installed .NET 5, please see a link below in the description where you are able to download the .NET 5 SDK. Note that you'll mostly be able to follow along even using earlier versions of .NET, but it is advisable to download .NET 5 to follow along with this tutorial and future tutorials. One of my core aims is to keep these tutorials right up to date. Please view a video created for this channel about the significance of the release of .NET 5. A link to this video can be found below in the description. So let's say that we wish to declare the assembly version global attribute in our code. We are able to do this by declaring this global attribute between the namespace declaration and the using directives. Okay, so why can't I see the assembly version attribute in the IntelliSense dropdown? The reason is that the assembly version attribute is part of the system.reflection namespace. So let's add a using directive to the system.reflection namespace. And now we are able to see the assembly version attribute along with other global attributes in the IntelliSense dropdown list. And we can now declare the global attribute against our assembly like this. So here we are attempting to set our attribute version number to 2.0.1 through the declaration of the assembly version global attribute. Great, so let's see what happens when we attempt to compile the code. So we have a compile time error. Let's look at our error list to take a look at the details of this error. The description of the error is duplicate system.reflection.assembly version attribute. So let's double click on the error item in our list that is causing the compile time error to occur. Okay, so a new file is open and we can see a red squiggly line under the offending code. It is a file that has a name that contains the assembly name followed by the suffix .assembly.info, and we are able to find this file within our projects directory structure. And if we look at the comments within this file, it is clear that this file has been auto-generated. It's in fact been auto-generated by MS Build. Let's navigate to this URL to read a bit about MS Build. The Microsoft Build Engine is a platform for building applications. This engine, which is also known as MS Build, provides an XML schema for a project file that controls how the build platform processes and builds software. Visual Studio uses MS Build, but MS Build doesn't depend on Visual Studio. By invoking msbuild.exe on your project or solution file, you can orchestrate and build products in environments where Visual Studio isn't installed. Visual Studio uses MS Build to load and build managed projects. The project files in Visual Studio .csproj, .vbproj, .vcxproj, and others contain MS Build XML code that executes when you build a project by using the IDE. Visual Studio projects import all the necessary settings and build processes to do typical development work. But you can extend or modify them from within Visual Studio or by using an XML editor. So the basic point I'm trying to make here is that many of these global attributes will be automatically declared in the assembly.info file when compiling your code using the Visual Studio IDE. You can gain access to some of these global attributes through the Visual Studio IDE. If you try to declare a global attribute, as I have attempted to here, you may get a compile time error because MS Build has automatically declared the global attribute in the assembly.info file. As we have seen, this results in a duplication of the relevant global attribute declaration, which ultimately results in a compile time error occurring. You are able to declare certain global attributes in the way we tried to declare the assembly version attribute. For example, let's declare the assembly description attribute. Let's comment out the assembly version attribute declaration. Let's add our own assembly description metadata to our assembly through a declaration of the assembly description global attribute. Let's pass a value of myAssemblyDescription to the constructor of the assembly description attribute. Note that depending on how the relevant attribute has been written, when the developer declares an attribute, the developer is able to provide custom metadata to the relevant attribute through the attribute's exposed public properties or the relevant attribute's constructor parameters. So, we know that the purpose of attributes is so that we can add or modify metadata against certain program elements or even against the assembly itself. Note that attributes on their own do not change application behavior. The metadata provided through attribute declarations can be read at runtime through the use of reflection. Relevant metadata can then be evaluated by our code, and appropriate code logic can be invoked based on the declared metadata. So this is how the Microsoft Docs describes reflection. Reflection provides objects of type. that describe assemblies, modules, and types. You can use reflection to dynamically create an instance of a type, bind the types to an existing object, or get the type from an existing object and invoke its methods or access its fields and properties. If you're using attributes in your code, reflection enables you to access them. Right, so let's use reflection to access and read certain metadata that has been added through the use of global attributes. So we need a using directive to the system.reflection namespace, which has already been included in our code. So let's write some code in our main method. Let's get a reference to the current assembly. We can do this by getting a reference to the program class's type and then assigning its assembly property value to a variable. We have named our variable this assem, referring to the current assembly. We can then get the relevant assembly name by using the assembly reference stored in the thisAssem variable and calling its getName method. And we can access the assembly's version information through the version property. Now we want to read the assembly's description, which should be the description that we included when we declared the assembly description global attribute. To get a reference to the assembly description attribute, we can call the getCustomAttributes method on the thisAssem object and pass in the type of the attribute of interest to us. Note that we are using the typeOf method to get a reference to the object type of the relevant attribute. Remember, attributes in C# are objects at runtime. An object instantiated from the assembly description attribute class should be the first item in our object array. We can use the as operator to cast the object to the assembly description attribute type. If the casting operation fails, null will be returned. If the operation succeeds, an object of the assembly description attribute type is returned. Let's write code to write out the metadata information about the current assembly that we have been able to retrieve through reflection to the console screen. Let's run the code. Great! So we have looked at examples of global predefined attributes. Let's look at some general predefined attributes. Let's start with the conditional attribute. Let's first add a new standard library project to our solution. And let's name our project Logging Component. Let's remove the automatically created class named Class1 and add a new class named Logging to our new project. Let's add a public static method to the logging class named LogToScreen. It contains one parameter named MSG and is defined as a string. The code for this method simply outputs the value referenced by the MSG argument to the console screen. Let's declare the conditional attribute against the LogToScreen program element. We have a red squiggly line because the conditional attribute is a member of the system.diagnostics namespace. So let's add a using directive to the system.diagnostics namespace. And now let's pass in an argument into the constructor of our conditional attribute. Let's pass in the text log_info. So what does log_info mean? Log_info is a piece of text that I've made up. This text represents a symbol in our code. We can use the define preprocessor directive and include the log_info symbol in our code. If the log_info symbol is defined using the preprocessor define directive within a file containing method calls to the log2screen method, the code within the log2screen method will be executed at runtime. However, if the predefined processor directive is not used to define the log_info symbol in the file where the log2screen method is called, its code will not be executed at runtime because we have used the conditional attribute to declare to the compiler that we would like this behavior to occur regarding the log2screen program element. So, the combination of the conditional attribute and the use of the define preprocessor directive can act like a switching mechanism, i.e. using this mechanism we are able to switch certain code on or off. This is especially useful for debugging purposes. If this is not clear, don't worry. We will demonstrate what is meant here through a code example. We are able to define our log_info symbol through the use of a preprocessor directive. We are going to use the define preprocessor directive for this purpose. Preprocessor identifiers are used to help in conditional compilation. If we navigate to this URL, we can see some of the preprocessor directives available in C#. For more information on preprocessor directives, please use this section of the Microsoft Docs as your guide. So here we have the hash define preprocessor directive that we can use to define a symbol in our code. So let's see how we can use a particular preprocessor directive in conjunction with the conditional attribute to conditionally output information to the console screen through our log2screen method. We must add our appropriate preprocessor directive code right at the top of our program.cs file in our code editors like this to implement the desired functionality. You can see we have the define preprocessor identifier in this line of code as well as the log_info symbol that we made up and passed as text to our conditional attribute which was declared against the log2screen program element. Let's include a using directive to our logging component namespace. In our main method, let's make a call to the logging.log2screen method and pass in the following text as an argument to the MSG parameter. This code is testing logging functionality. Let's run the code. And as expected, the appropriate text is written to the console screen. So, now let's see what happens when we comment out the relevant preprocessor directive code and run the code again. And you can see that nothing has been outputted to the console screen. Using our preprocessor directive, we can switch the execution of the code against which the relevant conditional attribute is applied on and off at compile time. This functionality can be very useful for debugging purposes. So, let's say we have a change to our logging component where we want all logging to be done to a text file rather than to the console screen, and we want the consumers of our code to use the method that logs the information to a text file rather than to the console screen. So how can we let the consumers know to use the log2file method rather than the log2screen method? We can simply declare the obsolete predefined general attribute against the log2screen method. Let's create a public static method named log2file. In the interests of time, rather than writing the code to actually log the value passed into this method to a file, let's just write code to output the value to the console screen and pretend that its method logs relevant text to a text file. Okay, so let's declare the obsolete attribute against the log2screen method. And let's pass a meaningful message to the constructor of the obsolete attribute. So we want any calling code that is currently using the log2screen method to receive the following warning message. The log2screen method has now been deprecated. Please use the log2file method instead. So now, if we go to our main method, we can immediately see a green squiggly line under the code that is calling the log2screen method. And if we hover our mouse pointers over the green squiggly line, we can see that the text that we passed as an argument to the obsolete attribute is presented to us. And note that if we want to force the user of our code to not use the log2screen method at all, we can set a second parameter in the obsolete attribute to true. If this value is set to true, an error is flagged when a user attempts to use the deprecated method, i.e. the log2screen method. Now you can see that the green squiggly line has turned into a red squiggly line, meaning that we no longer just receive a warning message. We are receiving an error message. This means we won't be able to compile the code. The last predefined attribute that I wish to discuss is the attribute usage attribute. We are going to create our own custom attributes and use reflection to read the relevant metadata added to relevant program elements through our custom attributes. So reflection and attributes will be implemented to provide flexibility to developers using our custom attributes to declare how relevant fields should be validated. This code is going to be very similar to the code that the ASP.NET MVC framework implements for field validation. In ASP.NET MVC, we can declare certain validation-related attributes against relevant program elements, and the MVC framework automatically handles validation of relevant fields for us behind the scenes, as it were. In this code example, however, we are going to create the custom attributes used for declaring how we want relevant fields validated, and we will also write code using reflection to read the attribute data declared against relevant program elements. In this case, the program elements will be properties. We will also write the validation code related to each of our custom attributes. Okay, so let's add a new standard library project to our solution. Let's name this project Validation Component. Let's delete the class that was automatically created by Visual Studio. Let's create a new folder named Custom Attributes. Let's add our first custom attribute class to the Custom Attributes folder. Let's right-click the Custom Attributes folder and add a new class. Let's name this class Required Attribute. Note that we must include the attribute suffix in the class name of our custom attribute. However, when we declare our custom attribute, you'll see that in the declaration we can omit the attribute suffix from the attribute name. We are, however, allowed to include the attribute suffix in our attribute declaration, but functionally this is unnecessary. We'll demonstrate this a bit later. The code for this attribute is very simple. Let's create a public auto-implemented property of type string named errorMessage. Let's add code to a parameterless constructor whereby the errorMessage property is set to a default value. So let's say we want a default error message of you cannot leave field, and then in curly brackets we have a 0 followed by the word empty. So the 0 in curly brackets allows the relevant field name to be inserted into the message at a later time. This is achieved through the use of composite formatting. If you are not familiar with composite formatting regarding string values, please view a tutorial created for this channel on C# strings. A link to this tutorial has been provided below in the description. Right, let's create a parameterized constructor. This will allow the developer to pass in a custom error message when declaring the required attribute against the relevant program element. The declaration of the required attribute will be demonstrated a bit later. In order for our class to be recognized as a custom attribute, we must ensure that our class inherits from the built-in system.attribute class. A custom attribute must inherit from the system.attribute class either directly as we are doing here, or indirectly. For example, if our class inherited from another user-defined class that inherits from the system.attribute built-in class. So now all that is left to do is apply the predefined attribute usage attribute against our required attribute class. Like with the obsolete predefined attribute, the attribute usage predefined attribute is a member of the system namespace. Basically, the attribute usage predefined attribute allows us to provide metadata to the compiler. That will tell the compiler which elements are allowed to have our predefined attribute declared against them. So we can apply rules or constraints through the use of the attribute usage predefined attribute against our custom attribute at the class level. This is an example of declaring an attribute against a class. So in the first argument passed into the attribute usage attribute, we can declare which program elements are allowed to be decorated with our custom attribute. So if we have decided that we only want our custom attribute to be declared on the following program elements, fields, parameters, and properties, we can declare this by passing in this code to the first parameter of the attribute usage attribute constructor like this. So here we are declaring which target program elements are able to be decorated with our required custom attribute. We can optionally set a property of type Boolean named allowMultiple through our declaration. If we set the allowMultiple property to true, this means multiple instances of our custom attribute can be declared against a single program element. We only want one instance of our custom attribute to be declared against a single program element, so let's set the allowMultiple property to false. We also have a property named inherited that we can optionally set through this declaration. Setting this property determines whether the relevant custom attribute is inherited by a derived class. In this example, we won't set this property. And that's it. We have now created our required custom attribute. So let's create our next custom attribute. Let's add a new class file to our custom attributes folder, and let's name this class stringLengthAttribute. Let's add 3 public auto-implemented properties to our stringLength attribute class. MaxLength, for the storage of an integer value denoting the maximum number of characters that a user can enter for a field related to a property against which the stringLength attribute has been declared. Error message, for the storage of a string value denoting the message outputted to the user when the user has entered an invalid value into a field related to a property against which the stringLength attribute has been declared. MinLength, for the storage of an integer value denoting the minimum number of characters that a user can enter for a field related to a property against which the stringLength attribute has been declared. So let's create a private method named setProperties that we can reuse for setting our public properties. This method will be called from a number of constructor overloads that we'll implement in a bit for this class. This method does not return a value and contains 3 parameters that correlate to the public properties that we have already created. The first parameter is maxLength, which is defined as int. The second parameter is errorMessage, defined as string. The third parameter is minLength, defined as a nullable integer. The question mark symbol following the int keyword denotes that this parameter is nullable. So, it is a nullable value type parameter, because it's defined as an integer, which is of course a value type. Let's also make our minLength parameter optional. We can do this in C# by simply assigning the relevant parameter a default value within the method definition like this. So if a value is not passed into this parameter, by default the minLength argument will have a value of null. Before we move on with our example, let's go to the Microsoft Docs, specifically to this location, to read a bit about nullable value types. A nullable value type T ? Represents all values of its underlying value type t and an addition of null value. For example, you can assign any of the following three values to a bool variable: true, false, or null. An underlying value type t cannot be a nullable value type itself. Very basically, a null value means that a value for the relevant variable has not been set. Adding a question mark at the end of the value type definition for a variable or a parameter means we have the option of storing a null value in the relevant variable or parameter. Note that optional parameters must be included at the end of the parameter list in the relevant method's method signature. Okay, so let's implement the logic for the setProperties private method. So firstly, let's check to see if the error message argument contains an empty string. If it does, we want to set a default error message value. In order for our error message to contain appropriate text, depending on whether the min-length value is set, we can create a nested if statement. So if the min-length value is null, let's appropriately set our default error message. If the min-length value is not null, let's include appropriate text relating to the min-length value within our default error message. So if the developer does not pass in an error message when declaring the string length attribute against an appropriate program element, a default error message will be used. For the scenario where an error message value is set when the relevant attribute is declared against a program element, the error message provided must be assigned to the error message public property of the attribute. Then let's set the max length property. This is a property value that the developer must pass in when declaring the string length attribute against an appropriate program element. Let's then assign the appropriate value to the min-length property. So let's use a ternary operator to check if the min-length argument is null, i.e. has not been set by the developer declaring the string length attribute against an appropriate program element. If the min-length argument is null, let's assign 0 to the min-length property. If the min-length argument contains a value, let's assign the value to the min-length property. So let's create our constructor overloads. Firstly, let's create a constructor that contains just the max length parameter. Then within our constructor, let's call our private setProperties method to assign values to the appropriate public properties of the string length attribute class. Okay, I also want to make the error message parameter in the setProperties method an optional parameter. We can do this by simply assigning default value to the error message parameter like this. Note that the parameter after the error message parameter in our parameter list is also the last parameter in the parameter list and is optional. So it is perfectly legal to make our error message parameter optional. Remember, the optional parameters must be included at the end of the relevant parameter list. Let's create a constructor overload that contains the max length parameter and the error message parameter. Then let's use our private setProperties method to assign values to the appropriate public properties of the string length attribute class. Let's create a constructor overload that contains the max length parameter and the min length parameter. Let's use our private setProperties method to assign values to the appropriate public properties of the string length attribute class. Note how we are passing in a value to the min-length optional parameter of the setProperties method. We need to be specific as to what parameter is being passed an argument here, because in this case, we are not passing in an argument to the error message parameter. The fact that the error message parameter and the min-length parameter are both optional means in cases like this, we have to make it clear which parameter we want to pass our argument to. Let's create one more constructor overload this constructor overload contains the max length parameter, the error message parameter, and the min length parameter. Let's use our private setProperties method one more time to assign values to the appropriate public properties of the string length attribute class. Let's ensure that we include the code whereby our class inherits from the system.attribute built-in class. So now let's declare the attribute usage predefined attribute against our string length attribute class. So we can copy the attribute usage declaration from our required attribute class and appropriately paste it in to declare the attribute usage attribute against our string length attribute class. Great, so we have now completed two custom attributes, the required attribute custom attribute and the string length custom attribute. Let's create one more custom attribute. This attribute will be responsible for indicating, when declared against a program element, that the input field's value related to the relevant program element should match a specified regular expression pattern. So regular expressions are great for defining patterns that an input field value must match for field types that must be constrained to a particular format, like, for example, postcodes, phone numbers, credit card numbers, email addresses, etc. So the validation code for fields like this will be simple. If the relevant input field value matches the specified regular expression pattern, the user's input is deemed as valid. If, however, the input field value does not match the specified regular expression pattern, the user's input is deemed as invalid. We can implement the validation logic related to our custom attributes once we have completed the code for this final custom attribute. So let's add a class to our custom attributes folder and let's name this class regular expression attribute. Let's create two public auto-implemented properties. The first property, named errorMessage, is of the string date type. The second property, named pattern, is also of the string date type. The pattern property denotes the regular expression pattern that must be supplied by the developer when the regular expression custom attribute is declared against an appropriate program element. Let's create two constructor overloads. The first constructor overload contains one parameter named pattern. The developer is able to pass an appropriate regular expression pattern argument to this parameter when declaring the regular expression custom attribute against an appropriate program element. The error message argument is not passed into this constructor, but we can provide a default error message in this constructor and assign it to the error message property. Let's create a constructor overload. This constructor contains two parameters, one denoting the regular expression pattern and the other denoting the error message. So this constructor allows the developer to pass in a regular expression pattern argument, as well as a custom error message to a declaration when declaring this attribute against a program element. So all we need to do within the constructor is assign the public property members of this class with the appropriate values passed into the relevant constructor as arguments. Let's ensure that we include the code whereby our class inherits from the system.attribute built-in class. The last step is to appropriately declare the attribute usage predefined attribute against the regular expression attribute class. This declaration will be the same declaration applied against our